Hello, can everyone hear me? I was here for some talks earlier and I couldn't really hear at the top. So can the people at the top, just if you hear me, just say some kind of positive signal? All right, great. All right, right on. So what I'm going to talk about here is very briefly, what is counterfactual? I'm going to explain what generalized state channels are very quickly, and then show you a cool demo of it working. Brief context on counterfactual. It is, as you see, it's an open source initiative to make off-chain applications much easier to build on Ethereum. The idea being layer 2 enables all kinds of phenomenal stuff, but it's really hard to do because there's no engineering and no software that's been put to actually make that easy. And so our goal is to do that as an open source project. My name, the clicker broke. Oh, let's go next. My name is Liam Horne. I'm the co-founder of a company called L4. We're essentially like a software engineering consultancy in a way, but we also help out in this community in all kinds of ways with ETH Global, which is happening this weekend, ETH Paris here, and we work on state channels research, plasma research, and a bunch of other stuff. Basically, we just really like Ethereum, and we want to help see this community grow. So, the goal of this talk, I briefly mentioned it, but I want to say, what's counterfactual? What are generalized state channels? Give you a demo, explain how the demo worked, and then let's do some Q&A and hopefully answer the questions that might have been confusing as I went through it. So, background. As you may or may not already know, state channels are basically the more generic version of payment channels. Lightning is starting to get very popular in Bitcoin because what it has done is said that, hey, instead of putting every transaction on the main chain, what if we could lock up some capital in a channel that is kind of like an escrow between two parties and then update the balances in the escrow. So kind of like a bar tab in a sense. And they turn that into a network to allow for off-chain payments. The same thing is basically true in Ethereum, that you can do that, but because we have a generalized state machine, you can do all kinds of more fancy stuff, which is what state channels represent to me on Ethereum. By the way, as a side note, I really like these type of talks to be very interactive, so if I say something that you feel like you don't get, and the people around you don't get, please just shout it out, and I want to make sure that everyone's actually getting the information that I'm kind of putting across. So, speaking of information, this is a paper that we wrote last year called Counterfactual Generalized State Channels. It explains in all the full detail exactly what a state channel is, how it should work from the most fundamental point of view. And so if you're interested in not just getting the high level, it's a bar tab where you move money between people really quickly, you want the full in-depth view, I recommend you check it out, l4.ventures/statechannels.pdf. That'll give you the full academic overview. So, what is a generalized state channel? I told you in Lightning we have a bar tab, you move money back and forth, and in Ethereum you may have seen there's Raiden, there's some other things that have basically enabled you to do off-chain payments. But what is it? What is this term generalized state channel? It's very specific, and I can show you in a couple diagrams. So basically a payment channel is this situation. You got a blockchain, there's a bunch of blocks being mined, and at some point you decide to put some money that you have in your Ethereum account into a contract with someone else that stores the balances that you have put in and that someone else has put in. And the idea is, as time progresses, not using the blockchain, but off the blockchain, like in person or over Facebook Messenger, or over some messaging, whatever it is, doesn't matter. You're exchanging signed messages between you and the other person saying, I owe you this now, and I owe you this now, and you just update that between you and the other party, right? And then whenever you're done, you feel like you've sufficiently incremented the balances between you and the counterparty. You get to the situation where now you have a new set of updated balances that you have and they have that's different from what the initial one had because you've been signing messages. And you put that on the chain and everyone gets their money back. So that's a payment channel. There's this term out there, application-specific state channel. Oh, my slide broke. Which is very similar. And so an example of this is if you may have seen tic-tac-toe in the blockchain and the state channel, or you may have seen in Funfair, they have this idea where you can put money in and you can play a poker, not a poker, but it's too complicated, but they can do blackjack and roulette and a couple of games like that. By putting money into a contract where you're not just updating the balances, like A balance, B balance, but arbitrary state objects. And then it's this exact same setup, you sign an update to the state, back and forth, and then whenever you've sufficiently gotten to this end state, you put that on chain, and you have a little bit of logic, this extra application logic, to allow for the money to get paid out according to what the state says it is. It's not just
give A bal, give B bal. It's take in this state, compute what A bal and B bal is. Okay? So that's an application-specific state channel. In our paper, in counterfactual generalized state channels, we introduced this concept of kind of the maximum you can go in terms of this technique using Ethereum. And we call those generalized state channels. The same setup. Alice puts money in, Bob puts money in, same setup. But instead of updating a state object, like some bytes array, you actually sign different commitments over time that represent new applications entirely off-chain. So what this means is that you can put money in a contract, and if you want to play tic-tac-toe, you can play tic-tac-toe, and the winner will get their money. And if you want to play a second game or a third game, or you want to do anything else, update payments, whatever you want to do with that money, the deposit you put on chain, whatever you want to do, you do that using a protocol that defines these off-chain applications. So you can have one, or you can have two, or you can have three, or you can have four, or you can have five, and the entire time there's no on-chain transactions. That's pretty cool, right? So anyway, that's useful. So this has been discussed for a while. This is like the researchy stuff. As time goes on, same thing, same situations are the ones you put the latest state on for whatever individual application you want to get your money out. So it's the same basic idea. But the main thing is you have multiple off-chain applications. So that's great. So that's a generalized state channel. What is counterfactual? The first thing before I dive into what we've built is I got to really just emphasize this point, because I think it's important, is that we're an open source project. There is no business called Counterfactual Inc. This is a project with multiple collaborators across the ecosystem, funded by the Ethereum Foundation at the moment, basically to build this as a public good for all of us to build dApps faster, better, so we can get to end users kind of as a community. It's a very simple mission. I've already said it a couple times. We want to make off-chain applications the norm. They should be. There's a lot of powerful stuff there, but we keep talking about it in conferences. We don't get to actual end users. So the goal is build a framework that can enable that to be done. So that's the mission of Counterfactual. But now the fun stuff. So how do we actually build something to enable that technique I just described to be possible? There's three core pieces, or three core layers rather. There's a couple pieces, but there's three core layers of the software. And I'll kind of show you a really cool picture here, and I can talk about it. Basically, I'll just say it first and I'll go through it. We're building an easy-to-use application library for developers that are building dApps to interact with Layer 2. An application library is something like Web3.js or Ethers.js or whatever it might be that you use to interact with a contract in the main chain. It's a very useful abstraction for building your dApps, and Truffle and these tools have enabled Web3 to proliferate. We're building a similar style library for Layer 2. So the same way that you would use a simple JavaScript library to build a dApp, you can use a simple JavaScript library to build a Layer 2 app. Additionally, because what I just described with regards to having multiple off-chain applications in the same state channel is kind of complicated, like you might be wondering, like, what do you sign, in what order, how do you actually do that? We needed to devise a protocol that the two agents, or the N agents if you go multiple people, speak to each other to ensure that every time they're signing something to install a new application or uninstall an application or update the state of an application, that is actually secure. So we've designed a protocol for that. You need to be running software that implements the protocol, and so that is what you would call the client node software. This is something that we've kind of packaged up, and that'll be shipping basically in, it's kind of the behind-the-scenes internal code, the same way that MetaMask drafts a bunch of logic to enable your calls using Web3.js to work. We have a bunch of internal code that we have that'll similarly run in your wallet to make sure that you're following the protocol. And of course, because state channels is a layer 2 technique, it's always possible that you may get into a dispute resolution scenario where you need to make sure that you can get your money back. And so we've built a very robust library of contracts and basically a flow for how you can get your money out if there is that dispute resolution that needs to be done. I'm not going to talk about the dispute resolution here. That's interesting from like the theoretical point of view, and if you're actually designing that kind of system, that's more the on-chain logic. I'm talking about the off-chain logic during this talk. So I'll show you a demo. I'll just show you something working, and then I'll talk about it. While I'm kind of doing this whole switcheroo, is there any questions? Anyone? No? Okay, sick. Where's my demo? I can't see it here. Oh, it's open QuickTime. Use QuickTime. This is QuickTime. Okay. I'm not going to risk it. All right, so let's go. So basically, let me get the setup here. And again, as I'm going, just feel free to throw out questions. There's a lot of detail here. So what's going on? So we have here two browsers, Brave and Chrome, and I have like the developer tools open. You guys can just look at that. But the setup here is that this is a website that is kind of that we've built as a demonstration of this whole technique that allows you to create an account with the website. And after you create an account, what you're going to see are multiple applications available to you to play against anyone else that's created an account. Does that make sense? So you can play any number of applications against anyone else that has an account on this website, all of which is 100% trustless, secured by the blockchain. So you'll follow along. I'm going to make an account on the first user's laptop. And what's going on here is that you're basically signing a transaction, signing a message with your wallet here to authenticate as this particular address that's on the website. This so far is pretty standard stuff. 2 users are going to do this for the demo. After you've signed in to kind of authenticate yourself, the server in the back end that I'll just talk about in a bit is kind of making sure that it knows who is who. It asks you to deposit some amount of money. So as I've just showed in the diagram earlier, you need to deposit money in from the main chain into your layer 2 environment. You're going to deposit some in here, 0.1, 0.1. And then what's going on here? So now it's creating your state channel. So in the diagram earlier where the Alice and Bob kind of swooshed into this layer 2 environment, this is the step that's happening here. We actually are running an additional state channel user here it's an additional user period that's actually deploying a multi-signature wallet on chain for you presently. So it's creating the state channel for both the left user 1 and the right user 2. This part takes a while because Robson is slow, so I'm just going to go past it. After it creates the state channel, it prompts the user to actually make their deposit. As a quick aside for folks that are in the know, this new opcode just got added to Ethereum called Create2, which completely augments that past step. So imagine if Create2 is implemented, then this would have been instantly what you saw when you clicked register. Unfortunately, Ethereum JSVM has bugs and they haven't implemented it yet, and so that's the state of the ecosystem. So you proceed to deposit some ETH into the state channel. This is still all the setup phase. Both users are going to do this. And, you sign a transaction that sends the money into the multi-signature wallet on both. And then what's happened is that you have put your money in to this multi-signature wallet. That's a bit of context. This multi-signature wallet is between you and our server in the back. So it's not between these two people. It's between each individual window and the server in the back. And after you put your money in, the server, because you authenticated earlier, and it trusts you blindly at this point, it says, okay, I'm going to also put in money. So the server's also putting in money. So you have two multi-signature wallets being created with the terminology for this is a hub. But it's another user, it's our user, and I'll talk about what the tech looks like in a second. And after a while, after Ralston blocks get mined and it confirms the transaction and whatnot, which takes a while because test nets are slow at the moment, at least this one is. Eventually, the UI says, great, it's collateralized, you have put your money in there, the hub has put their money in there, and you can now use this layer 2 generalized state channels demo. And because I showed you in the slide earlier, you can have multiple apps. We have multiple apps available for people to play. And it's very simple. I have to add a quick dev parameter here to make sure that these two match make, so let me just go past that. You open up one of the applications. It's very simple. You put in your sub deposit. So remember, we just put in a deposit of real ETH from the main chain into the multisig. And now what it's asking you to do is put in a sub deposit, an off-chain deposit, into this new application, which is a layer 2 application. So you say, hey, great, I want to put in 0.001 ETH, 1/10 of my total balance, and I want to bet it against user 2 in a game of tic-tac-toe. User 2 gets messaged, and it says, hey, this guy wants to play with you, do you want to play him? And he says yes. And all of a sudden, the game loads. There's a weird bug there in the UI, we'll fix that. So, the game loads, and so what just happened? Neither of these two people have a state channel with each other on the main chain. But they have a state channel with this hub, which I'll show some slides in a second how that kind of works, that has enabled them to play a game against each other off-chain. And so, this could work between any number of accounts. So, if you guys open up a laptop and make an account, I could click, I want to play against you, and play against you as well. And then, obviously, with the state channels, all of these moves that are made, these state updates that are happening in the application, are kind of following the protocol where you sign the move that you're making, you send it to the counterparty, they get it, they make sure it's the right thing. Once they validate it, they then render the new UI. And this guy wins. He's very happy. Coins are drawn. And you can see the balances get updated there. So this guy just was essentially paid based on arbitrary Turing-complete EVM logic in an application for which he has no relationship with this other guy at all. So it's off-chain, layer 2 conditional payments, all of which is 100% backed by real Ethereum transactions that in any scenario, malicious or just honest, you can get your money out and it's yours. So that's pretty cool. So yeah, that's most of the demo. I could keep going here and I could play a bunch of other games, and when we launch this in a couple days, you'll be able to see, you can play this dice rolling game as well, and that one's pretty fun. And yeah, there you go. So that's the demo. Any questions on the demo? Yeah.
Can you just explain, what were the on-chain transactions?
Yeah, so the on-chain transactions, I think I have a slide which will kind of generally show it, is that you deposit money in, I can show you from a second ago. This one. So the filled lines are on-chain transactions. So what you did is you deposited money into this multisig from both sides. Alice is the server that we're running, the hub. Bob is the window, the user, right? So it was deposits. There's one extra step that happened in the background. You didn't notice it because it was happening on the server, is that a multi-signature wallet was deployed, which is how the contract gets on chain in the first place, by us, the server. And I was saying a bit of an aside earlier that with create 2, a new opcode, is now, that step is gone because the contract is counterfactually instantiated, which is a fancy term you guys can Google and maybe we'll write about to clarify. Yep.
You said that in any circumstances, malicious or otherwise, you get your money back.
Yeah.
Thanks. How have you verified that, and how can we verify that?
Yeah. So we haven't done like security audits yet, but well, two answers. So first of all, we haven't done security audits yet, but what we've done is we've defined a very specific protocol, all of which is documented, I would say like a 7 out of 10. We're going to improve it over the next little while, way on specs.counterfactual.com. Effectively, there's each party, like Alice and Bob in this case, and the intermediary, which is not shown on this slide, sign particular commitments, sign messages that are transactions to a particular contract we have. And I mentioned earlier, I don't want to go into too much detail here because that whole thing could be a talk on its own. And basically, as you sign these particular commitments, every step along the way, you always have something that is in your possession that could be put on chain to this contract we have. It's called an app registry to get the money out. Maybe we can talk after because it does get pretty convoluted and all the code is open source. You can see it all on a repo, and I'll talk about that in a minute. But basically, yeah, the protocol we designed is designed for that. Yeah. Good? Okay, cool. So that was the demo. So what did you just see? So I've explained it as I've been going along, but this stuff can be complicated, so I'm going to kind of just be very explicit about what it was. So you saw this screen. What it was kind of a couple things. A demo site, first of all, this is a bit of a technical explanation, of an engineering explanation if you want. We have a demo site. So I'm kind of highlighting this region because what you actually just saw was not one kind of monolithically built React app or anything. This was actually engineered in such a way that the external environment here is its own software, kind of similar to kind of a wallet like a MetaMask, that's running the state channel node, that is the thing that is implementing all of the protocols that I just alluded to a second ago. And that thing itself is rendering iframes inside the window. The iframes are implemented using your favorite front-end app of choice, create React app or Stencil or Ember or whatever it is you want to use, using an API that we've designed, the developer library from the slide with the three triangle layers there, that communicates to this wallet-like environment, the node, to speak to the methods that it exposes to do things like install an app and update the state of the app and place your tic-tac-toe, right? Take an action on the state. So that's what's going on there. And this is kind of what that looks like. You install app. After it's installed, you get an event that's given to your app and you update it. And the point I'm making here is these are very separate components, very easily separable that you can explore. And if you want to build your own app, is designed for that scenario. You notice that I deposited and withdrew at one step. That's because literally this is an iframe container, there's no way we have access to your private key. We need to go to MetaMask presently to go and say, hey MetaMask, we want to deposit money. Can you sign this transaction to deposit money into the multisig? Does that make sense? And the really cool thing here is that the whole thing has been designed with the expectation that wallets will eventually have layer 2 compatibility. And so, give me a second, I'll go back in a second. And so what we're going to eventually be doing, very soon in fact, we've already started the spike work, is integrating this directly inside of MetaMask. So MetaMask has a speculatory layer 2 environment that it's building right now. We're kind of working very closely with them on that. And you can imagine in the future, you're going to have these layer 2 apps that you can access to do whatever it is you want to do in layer 2. And this will be natively implemented within MetaMask. So anyone with a MetaMask account also has the ability to use generalized state channels, any app, anytime they want. I want to make a very just quick thing here that I wanted to add at the last minute. This is what the code looks like. When I'm saying developer API, I literally mean like this. This is a React handler. So like you click on a button, and that button executes some JavaScript. This is that JavaScript. It literally will take the coordinates on the tic-tac-toe board in this scenario and call this method, the highlighted method, an object that we have instantiated locally for you to use. Kind of like in Ethers.js and in Web3, you have a contract object. In this layer 2 environment, we have an app instance object. And you just take your action. And you literally give it an action, like, hey, I want to place my X or O, depending on who user you are, in this coordinates. And if I want to claim that I've won, I can claim I've won. That's just the way this particular app has been designed. So this is an arbitrary action struct. But anyway, I just want to get that point across that it's literally a developer library you plug into your application for this stuff, and it's made specifically to be easy to use. Okay, so great. What about all this stuff I'm talking about? Producing signed commitments. There's some representation of a state channel. What is that? Presently in the demo, we literally stored all of that in your local storage. It's a pluggable storage infrastructure, as you probably expect, but this is kind of what it looks like. And here's I think I have a quick example. And here's kind of what the data looks like. I'm not going to go into all the depth here, but literally you're storing a state channel object, and this is the array of app instances you have. And you have all this useful information. Let's see if I can mouse over. You have all this useful information. For example, what is this app? In this particular case, this is not the tic-tac-toe app. This is a different app, which is a two-party payment channel app. And again, there's probably a lot of questions in the specifics here, but I want to just get the main point across that this is a simple structure that we use for all arbitrary types of applications. In this case, a payment channel where you have Alice's address, Bob's address, how much Alice has, how much Bob has. And then you have the state of that as of now. So in this case, Bob seems to have a lot of money. And so, yeah, all of this stuff is just stored locally in a very simple to read, immutable data structure that gets updated by our node. And you have access to it in your application or your wallet if you want to build a wallet around this too. So there you go. So the final point, this is all running on my laptop. And I was playing against another window in this demo. But in a future version of this talk, I'll probably do like 2 laptops, and I'll play against someone else remotely, or maybe someone in the audience or something. But there's 2 laptops, and they're communicating, as you might expect, through some communication channel. It doesn't need to be any particular one. We could use libp2p, we could use WebSockets, or if you're like very, very reckless, you could use Firebase. And the main thing, as I kind of alluded to a second ago, multiple times actually, is that they played each other by using a hub. And the way that kind of works is that we have 2 state channels, my laptop, the other laptop, or my window, the other window. There's no channel between them. And so we have a third node running that effectively collateralizes by having a channel with each of them already. I've already talked about most of this, so I'm kind of going through a bit quickly here. and it instantiates something called a meta channel, which you can read about in our paper, and there's also another thing called a virtual channel, which is a much more formally specified version of this, basically allowing me and Nima, which is the example name of the other person, to play this game of tic-tac-toe against each other. So that's kind of how that works. And the cool thing is that Hub, I'll get into a bit of detail here, is literally running the exact same code as this laptop, the other laptop, and there's really no difference except instead of storing data in local storage, in this demo specifically, I think it stores it in Firebase. It might store it in the file system, I forget. But it's the exact same code. So there's no special hub infrastructure and client infrastructure or anything like that. It's just different nodes. So you can keep extending this. They message each other over the messaging protocol to propose the message. There's no need to involve the intermediary at this point. And then when you want to install the virtual app, you just send a simple message over to the intermediary saying, I want to install this virtual app with this person. The protocol, which I alluded to earlier in specs.counterfactual.com, if you want to read about it, executes in a particular way to make sure that everything's collateralized, and you get to play tic-tac-toe. So, yeah, that's the demo. That's the talk. Yeah.
Hi, thanks for the talk. So can you go a little bit more in detail on what happens when they go from the state channel back on chain? What happens with all the transactions, and how does this
yeah,
go in
so the way that layer 2 works is that you accumulate an enormous number of signed messages from particular people that could in the future be dishonest, so that if they are dishonest in the future, you can use those specific signed messages. But if they're honest, then there's usually a different type of exit mechanism to get the money out. So in our case, if you want to, I should have had the withdrawal in the demo. If you want to withdraw your money, because these are just multi-signature wallets, you literally just say, hey, Hub, I want to withdraw my money. And he says, okay. And it's a multi-signature wallet send. It's just a multi-sig. You just send the money out. If he doesn't say okay, well, then that's when it gets into the more detailed scenario, like you mentioned, where you need to pull out the commitment that you previously had saved in your DB from when he signed it earlier. And then you put that on chain. You wait some time because he might have a later commitment and you might be the one lying. And then basically there's a dispute resolution mechanism. I don't really want to go too much into that in this talk, as I mentioned, because it really is like the whole thing. If you want to read about it, all the code is in our repo. It's at GitHub/counterfactual. The specific contract is called the app registry, and you can read how that works. We'll probably write about it, maybe do a video about it, and I'll put it on YouTube later. But yeah, it's just you put the signed commitment on chain. You wait for a timeout. You know, they might challenge you and say, no, I'm the one lying, and then but there's a whole resolution scheme basically. Yep.
Hi, thank you for speech. I have 2 questions. What do you think about what will be incentivization of hubs? And the second one is, what do you think about future, about growing of state channel networks? Will be, it will be growing around hubs or like such as mesh networks in internet?
The first question was, what do I think about synchronization of hubs?
Yeah, no. In your thought, will be any some kind of incentivization of hubs or no? What?
I don't really get the question. Can you like say it clearer?
What motivation of hub?
The motivation of hubs? Oh yeah. So this is the same as any other thing, right? Like any other state channel network is that usually if you're adding payments to them, you would take a fee on the payment. And you know, if someone's offering a free service, they'll just do that one. But if there's no free service, then you have to pick the lowest one. It's like a market, right? You just got to pick whoever's going to give you the lowest fee. The hub doesn't need to do this, right? So the idea is the same as Lightning. They pay a fee. And it's a bit more complicated in this scenario because in Lightning, the only function you can apply is send, right? It's like it's instantaneous send. But in this case, there's more complicated functions, and so the time is longer than instant. For example, in the tic-tac-toe game, the hub is not just like doing a one-time payment. The hub is holding money for the duration of the tic-tac-toe game. So the time is like, you know, whatever that was, 30 seconds. And so what the hub will do is the hub will say, okay, I'm going to loan you this money, essentially. And it's not really a loan because it's trustless and non-custodial, but I'm going to quote-unquote loan you the money for 30 seconds, and you pay me this much per second, something like that. and you pay the hub through a state channel itself. In the whole stuff we've built, we haven't added in fee infrastructure or anything. That, interestingly enough, actually can be built on top of everything we've built as an additional app itself. So yeah, it's not really something that I have some opinions on it, but I think people will build apps and there'll be different types of mechanisms that are tried out. Yeah, was the other question up there somewhere? Oh, he's coming down with the mic.
Thanks. I wanted to ask about the sort of on-chain component. So I guess if you write some app, you want some sort of smart contract that can act as a sort of arbiter of last resort if there's a dispute. Could you speak a little bit to the API or how that looks?
Yeah. So how much time do I have? I have a few minutes. So in a previous version of some talk that was like, this is a morphed version of, I had some slides on that. I might have it open in another tab, so let me just see if I do still. This is live craziness. Maybe here, DevCon. Yeah, I do have it. Look at this. 1 second. Okay. So I'll give this part really quickly. So the basic idea behind the framework is that there's certain types of applications that work the exact same way every single time, regardless, in a generalized state channel use case. And those set of applications are state machines, which have pure deterministic state transitions with no conflicts between how those transitions can be made. So that's kind of like state machines like this, where you have a state that you're in, a transition that you can go to based on some rule. For example, you might be in a state where you have its X turn, and if it's X's turn, one of three things can happen. X can go, and then it's O's turn, or X can go and then it's a draw, or X can go and then he won. Right? It's a pure deterministic finite state machine, effectively. There's some subtleties there about like who can go in what order, and you can't have two people going at the same time, but generally finite state machines is a category of applications for which this works, and pure ones where there's no necessity to read on-chain state. If you do read on-chain state, you can handle this, but you have to be aware there's some extra risk parameters, and you have to add extra software for those cases. In our deposit case, we actually have a custom-built app that does do that, but for most cases, pure finite state machines will work. And so I'll show you the code. This is not tic-tac-toe. This is a different one, which is even simpler. It's a state machine where you have a number, and the one function is update the number, right? So it's like a circle, and you can update it. So in this case, you literally write your application like this. It's a stateless contract that has no storage. So we're simply using the contract for the reason that it's easy to write Solidity code, developers know it, and you can put it on chain, use EthCall to generate a transition, but there's no storage on this contract. It's just EVM logic using Solidity. So here's a contract. There's more detail here. This is the contract. You define your app state using ABI encoder v2 structs like this one. So in this case, it's player 1, it's player 2, is what's the number, and whose turn is it? The action is increment or decrement, and by how much? So there's a little bit of extra stuff than just send, than just add. It's like add or decrement by 1 or 2, 3. Yeah, there's a function called apply action. If you know Redux, it's very similar to that. The idea is you take the current state and an action, and then you figure out what is the transition. And this function can throw, right? You can throw errors, and if it throws an error, then it's an invalid transition. But if it doesn't throw and it returns a new state, then it's a valid state. So this is what the developer writes of the application. So, it's like Redux, literally, like give it some state, increment it, decrement it, do whatever the hell you want, and give me a new state. And if it doesn't throw, that's your state machine. This is just the implementation detail using Solidity, +1, -1, or whatever. So, yeah. Does that answer your question? Cool.
Thank you. I have a related question to this. So this state machine is executed on the client, just so there is no proof that actually the game rules were satisfied at the end of the channel, right? So can you prove that they played according to the rules?
Yeah, you can. So
You can?
you can, yeah. What's the best way to answer that succinctly? So you agree on this ahead of time. You agree on those rules. There's two ways you can agree. The first way that you can agree is you can agree on a contract address on chain that is this contract, and you say, if we're going to play an application together, we're playing this one. And I say, are you okay with that? You say, yeah, I'm okay with that. We sign a message saying that we're going to install that specific contract address. And so when I sign an update, I use the code in this contract to generate my transition. I send it to you, and you say, okay, well, we agreed on this contract earlier, so I'm gonna run it myself too, also, my own way. And if you get the same output, and that's what I signed, you know it's legit. The second little subtlety there is, if it's not the address of an on-chain contract, it could be the hash of the bytecode, which you could also use. And then in the case of a dispute, if you do that, then you also have to deploy the contract on chain. But this is more of a subtle detail than anything. More important is that you agree ahead of time on this logic, and you literally sign a message saying that this is the logic we're going to use. And you then locally verify that it was used. Yeah, it's literally the same contract in the enforcement mechanism. It's exactly the code that will get run. Up there.
Do you really need the hubs, or are they more just there for scalability reasons? And so, like, each.
Sorry. Do I really need what? Sorry.
Do you really need the state channel hubs, or are they more there just for scalability reasons, so that there doesn't have to be direct connections?
No, I'd say they're more. I mean, I guess that's one reason. I'd say scalability reasons less so than usability reasons. Like, if I wanted to, if you and I happen to just meet each other and we want to do something that requires a state channel, and we don't have any connection to anything anywhere, then we have to go through this whole like open channel procedure where we deposit money in and then we do the thing. But if by chance you know another person that I also know, in the sense that we both have a state channel with them, then we can just do the technique I showed with no on-chain transactions at all. So it's way more usable. It's the same reason why Lightning Network needs to be this massive network, right? If everyone if there weren't like some easy path between any other person, then you have to do a deposit. So it's usability.
Right. So the hub isn't necessarily like this dedicated thing that's a hub. It could just be another.
Yeah, it's just a
person
node. It just
Okay.
so I mentioned we're running on Heroku, the exact same software that's running on this laptop, and it just so happens to be the case that the website that you saw is also hosted by us, and so we're hosting a website and a node that conveniently with this UI we allow you to use for the purposes of playing these games.
Okay. Thank you.
Yeah. I think I'm out of time, am I, or do I have more time? 5 minutes? Okay, do we have 5 more minutes of questions, or?
Okay, so, hey, if I have a channel open with you, where do we store the signed data once we have like interacted a bunch of times?
Yeah, that's a good question. So, I mean, I did kind of answer in the sense that it depends where you're running the software. Like, we've designed it to be modular. In the case of it running on your laptop in a browser, presently it's local storage as of the current demo website, but it can literally be anywhere. Presumably, if you're going to run this in production, and as we build out more examples and demo and default options, it'll be more production-ready environments. We might offer a service. You could choose to. There's lots of ways you can store it, basically. Yeah, like the easy answer is just like store it in MetaMask, but there's no hard requirement, basically.
And do you have a plan for services that help you solve disputes if you're offline?
Yeah, so there's this cool project called PISA, which was funded by the EF. They are a group of people that have done both interesting research on a full decentralized kind of watchtower service, but they're also just building like a useful service in the interim that might not be fully decentralized. And so they're already engineering parts of this. We might just use that if it gets shipped quickly enough. If not, then we'll write like a simple service for this. We're not really trying to build all the additional production level software immediately. We're trying to incrementally just grow this project, and maybe some others will choose to build a production service. But as time goes on, more production services for all of these things, storage, watchtowers, all of that will come about. Ideally, for the end developer, it's still just as simple as like write your app, don't care about anything because there's really good sane defaults, and move on.
Cool, thanks.
That's again in the middle.
Could you talk about maybe some future steps towards state channels without on-chain deposits and withdrawals, such as being run on a sidechain or a plasma chain?
Yeah, so basically, so you're kind of alluding to like using a plasma chain or a side chain there. From the point of view of everything I just talked about, it doesn't matter what the chain you're using is at all. In the case of all the software we've written, it's designed for an EVM compatible chain, but it doesn't really care what the chain is. As long as there's some way to describe using Ethereum, in EVM codes, as long as there's some way to describe it, then you can use that in this system. So for example, if you wanted to store a coin on a Plasma Cash chain, then instead of referencing in the state deposit as being on-chain ETH at this address, you would reference the state deposit as being a coin in this chain, which is just a different, it's a different set of EVM code. Instead of doing address contract.balance, you would say plasma chain contract.getMyCoin this address. This definition of the funds that you have in your state channel itself is arbitrary Ethereum transactions. So, and that's a whole other thing that I could get into as well, is that this is fully generalized, not just for like ETH or tokens, it's arbitrary transactions. So, you could be playing a game where the outcome is not you get ETH, the outcome is that you get a signed message produced that said that you beat somebody at chess. And that updates a leaderboard if you can produce the signed message in some, IPFS server. So there's all kinds of crazy stuff you can do. Anything you can do with Ethereum, you can do with the state channels between the finite sets of people.
Just one question about if two people start a game like this, they open a deposit on a state channel, and now, let's say one of them contact the main chain and takes out and bail out, but before it does it, it continues to play with the other player. So the other player still thinks the money is there, so he continues for at least one block on the 20 seconds to play. So in a way I can cheat and steal you some money that I...
Well, the answer to your question, is there any way I can cheat and still lose money? No, if the software works. That's the initial answer. The second answer is, so basically you're wondering like what happens if you put on a challenge and you don't realize the challenge has been put on chain and you keep playing the game or the application and the state is somehow invalid because the challenge began on chain. The first thing to note is that if someone puts a challenge on chain, a useful property is that that challenge is the time period, let's say like 7 days. Even if you don't notice for 7 days, you can keep using the application, and as long as at some point within those 7 days you take some latest signed state and put that on chain, you're good. So what you need is just to make sure that if someone ever puts a challenge on chain, you, at some point within the timeout window, put a rebuttal to the challenge on chain. And for that, you want software that does that for you. That software is typically called watchtowers. That's what Pisa is building, and that we're also going to build probably some very simple MVPs for. And if that software works, then you can't lose money. Any more questions, or are we good? Okay, cool. I have 2 quick slides just for reference if you guys are curious, assuming it still works. If you want to learn more, you can go to our GitHub, github.com/counterfactual. All the code is there. You can audit it. We have issues if you want to help out. Just add an issue. We have a Discord as well. You can go to counterfactual.com/chat. Yell at us if something's broken or whatever it is that you want to yell at us for. And there's a website, which pretty bare bones, but it gives you the general idea of what the project's about. So that's us. Thank you.